Hello everyone, I am Madhuri, working as an assistant professor in the Department of EEE at MLR Institute of Technology. Today I am going to discuss about DC generators. In that the contents goes like this. First I am going to discuss about the working principle of DC generator. Then I am going to discuss about the types of armature windings. Then I am going to discuss about the EMF equation of a DC generator, how to calculate the EMF equation of a DC generator, and what is the respective mathematical equation of a DC generator. So first, stepping into the working principle of DC generator, we first basically discuss about Faraday's laws of electromagnetic induction. Faraday's laws of electromagnetic induction basically states that when a current coil conductor placed in the presence of a magnetic field, when the magnet is stationary and if the current coil conductor is rotating, there will be a deflection shown in this connected galvanometer. That deflection shown in the galvanometer is nothing but the EMF induced in this current coil conductor. In case 2, when we put the magnet as a moving and the current coil conductor is stationary now. In both the cases, there is a deflection being shown in the galvanometer. This deflection shown in the galvanometer is nothing but the EMF induced in this current coil conductor. This EMF induced in this current coil conductor will allow the current to flow in this conductor. So, in Faraday's laws of electromagnetic induction, we have two cases. Case 1, when the magnet is stationary and when your current coil conductor is rotating or moving, there will be a deflection shown in the galvanometer connected to the current coil conductor, which is nothing but the electromagnetic field. This electromagnetic field is responsible for the production of current carrying conductor. In the case 2, when the magnet is moving and this coil is stationary, there will be again deflection shown in the galvanometer in this current coil conductor. So this EMF is again responsible for the current which flows in this conductor. So in both the cases, the EMF generated is directly proportional to the flux linkages of the magnet in a particular stipulated time. So this is the relation, basic relation for Faraday's laws of electromagnetic induction. And the working principle of DC generator involve the Faraday's laws of electromagnetic induction. As discussed in the previous slides, we have two cases, that is when the magnet is stationary and when the carrying conductor coil is stationary. So in both the cases, we consider the dynamically induced EMF as the working principle of our DC generator. Dynamically induced EMF is nothing but when the conductor which is rotating in the presence of magnetic flux, stationary magnetic flux, if the conductor cuts the stationary magnetic flux, there is a dynamically induced EMF produced in the same current carrying conductor. This EMF causes the current to flow in that respective conductor. So when the circuit is closed, when this conductor circuit is closed, there will be a response. This EMF causes the current to flow in that particular conductor. So this energy conversion principle, which is involved in working principle of DC generator, is nothing but dynamically induced EMF. This dynamically induced EMF is produced when the rotating conductor is placed in the presence of a stationary magnet. That is nothing but this rotating conductors are placed in the armature of our DC generator, which we have discussed in the construction of DC generator. So the amount of EMF generated is given by the equation E is equals to d phi by dt, where phi is the flux linkages which are produced due to the magnet and t is the respective time in which the entire process has took place. So basically in DC generator, the working is affected by presence of two main important parts. One is the magnetic field which is there in our core, that is nothing but the yoke part. We have stationary magnets to which the field windings are connected. And we have conductors. These conductors are placed in the rotating part, that is nothing but the armature. So when these conductors which are present in armature rotates in the presence of a stationary magnetic field, an EMF is produced with the help of basic laws, Faraday's laws, and the generated EMF in that conductor will cause a current to flow through it. So this can be seen in the figure. So in the first figure, we can see we have a north pole and south pole. So this part which is in yellow color is nothing but your magnetic field or magnetic flux lines. The direction of magnetic flux is from north pole to your south pole. I am placing a coil, naming it as A, B, C, D, in the presence of this magnetic flux. Initially, the coil is in this position. So when I start slowly rotating this coil, the direction of the coil sides gets changes in this way. In step number 1, we can see the A, B, C, D of this current carrying conductor coil when it starts rotating. So now in this step, this coil is parallel to the direction of magnetic flux. So in this case, the EMF is nothing but d phi by dt, and this value of EMF when the coil and the magnetic flux are parallel to each other, it is maximum. So maximum value of EMF is attained when the current carrying conductor is parallel to the magnetic flux direction. So we can see the direction of magnetic flux with this red arrow and the direction of induced current in both the sides of the current carrying conductor coil in this way. As the conductor is a closed circuit, so this magnetic field, stationary magnetic field, is responsible for the production of current in this coil. Moving to the next step, when we put the conductor coil perpendicular to the direction of magnetic flux lines, the EMF is perpendicular and the EMF induced will be 0 at this particular instant of time. And the direction of flux when there is no EMF induced in the current conductor, so the current value is also 0. That is why you cannot see any direction of current or current flowing in the coil or the conductor ABCD. And moving on to the next step, again, the coil sides have come to the initial position after one complete rotation. In this position also, the magnetic flux lines and the conductor are parallel to each other. So in this case, again the EMF is given as d phi by dt, and the value of EMF is also maximum in this position. As you can see, the direction of flux, which is given by this arrows in red color, and the direction of induced current in the coil sides or the conductor sides is given in green color. So now the direction of currents in the closed conductor are given by Fleming's left hand rule. In real picture, when you cut down the machine of a DC generator, you can see the conductor is attached to the slip rings. That is nothing but your brushes. Brushes are given as B1 and B2 here. So brushes which are again connected to the commutator. In commutator, the current which is flowing in the conductor coil is AC. This commutator converts it to DC. And from the brushes, the current is delivered to the external circuit. You can see the direction of flux here when at different instants of rotation. These brushes B1 and B2 will collect the unidirectional current from the commutator at the end of current carrying conductor coils in this way. This is the waveform of unidirectional voltage which is produced at the ends of the brushes, which is delivered to the external DC circuit of your generator. This is the whole working principle of DC generator discussed in different instances of coil rotation and what are the respective voltages EMF induced in that particular instance are also discussed in the previous slides. Moving on to the next slide, we discuss about the types of armature winding. In armature winding, we basically have two types of windings. Windings are connected in lap and in wave. We know that armature is the rotating part of the DC generator. In which we have the armature coils. These coils in turn carry the current I. So now in lap winding, your conductors are connected in such a way that the end of each armature coil, if you consider this as coil 1 and coil 2, which you can see in the picture, the end of coil 1, the starting end of the coil 1 has started in commutator segment 1 and the second end of the coil, same coil, has end in the commutator segment 2. So in lap winding, we connect the conductors in such a way that the starting end is connected to one segment of commutator and the second end is connected in the adjacent segment of the commutator. Here, number of parallel paths are always denoted by A, and here the number of parallel paths are always equals to the number of poles. These lap windings are again subcategorized into simplex lap winding, duplex lap winding and triplex lap winding. Based on the connections and the number of coils, we classify this lap winding into three main categories. So first one, simplex lap winding, second one, duplex lap winding, and the third is the triplex lap winding. In the simplex lap winding, we can see that the first end of the coil has started from commutator end, commutator segment 1, and the second end of the same coil has end in the adjacent segment of the commutator. So in this way, the connection goes on with the different coils in the armature. This kind of connection is nothing but the simplex lap winding, or basically it is the type of basic lap winding connection which we do in DC generators. These simplex lap windings are usually used for low voltages applications. So we connect the conductors in the armature using simplex lap winding for all the low voltage applications. Next one, we see about the duplex lap winding. Duplex lap winding is nothing but, in the duplex lap winding, the number of parallel paths between the pole is twice the number of poles. Parallel paths are again the paths for carrying the current. In duplex, as we see in the name, the number of parallel paths between the pole is twice the number of poles. So, if we consider north pole, the number of parallel paths are twice the number of poles. If you consider one pole here, we have two parallel paths in which the two conductors are carrying the current. And coming to the lap winding connection, the starting end of the coil has started in the commutator segment 1 and the second end of the same coil has end in the commutator segment 2. So here the parallel paths, the number of parallel paths, we have twice the number of parallel paths under each pole. In simplex lap winding, we have one parallel path for carrying the current under one pole, but in duplex lap winding, we have twice the number of parallel paths for carrying the current under each pole. Duplex lap windings are used for heavy current applications. Such type of winding is obtained by two similar windings on the same armature, connecting the even number of commutator bars to one winding and odd numbers like the conductors 2, 4, 6, 8 are connected to one segment of the commutator. The conductors 1, 3, 5, 7 are connected to the another segment of your commutators. This is how we do the duplex lap winding. We usually use this duplex lap winding for heavy current applications. And the last, triplex lap winding. These windings, if you have commutator segments, so 1/3 of the commutator bars are connected to the coils. So this is the entire commutator segment. In this, 1/3 of the commutator segments will be connected with the windings. In this, we have many parts because one segment may have many number of conductors. That means there should be many parallel paths to carry the current under the same commutator segments. So these are used for larger current applications again. The only disadvantage is if we have number of conductors or windings under one commutator segment, which increases the number of conductors, which again increases the cost of the windings. So the DC generators which are employing triplex lap winding are basically used for larger current applications, and they are also very costly machines as a material used for the conductor coils is high. Moving on to the next, we have second category of winding which we do in armatures. It is nothing but the wave winding. So in wave winding, we simply connect the conductors in form of a wave. That means the first end of first coil and the second end of the same coil will be connected to the first end of the next coil, which is under the influence of the same poles. First, if we have two ends for a conductor, consider this as a coil 1. This is the first end of coil 1 and this is the second end of the coil 1. We can see the second end of the coil is connected to the first end of the next coil. So end of coil 1 will be connected to the starting of coil 2. So in this way, we make the connection in the form of a wave. So the name itself indicates the connection of the armature conductors are in the form of wave, and this is nothing but wave winding. This is how we connect the conductors under each pole in wave winding. The finishing end of one armature coil is connected to the starting end of the next armature coil in the commutator segment at some distance apart. All these are the commutator segments in which the respective armature coils are connected in the form of wave. In this winding, conductors are connected to two parallel paths irrespective of the number of poles of the machine. How many? Irrespective of the number of poles, the poles may be of 2 or 4, but all your conductors are connected in two parallel paths. So here the number of brushes is equals to the number of parallel paths. Obviously in DC generator or a DC machine, we have two brushes. For a wave winding, your parallel paths is equals to the number of brushes. The wave winding, we can use it in high voltage and low current machines. Its applications are mainly in high voltages and low current machines. And in lap winding, your number of parallel paths will be equals to the number of poles. In wave winding, the number of parallel paths are equals to 2, which is nothing but which is equals to the number of brushes. Moving on to the EMF equation of a DC generator, let us consider phi as the flux per pole. If we have two poles, north and south, let us consider the phi as flux per pole in Webers and the total number of conductors as Z. Total number of conductors are nothing but the conductors which are in the rotating part of the DC generator, which is nothing but armature. Let us consider Z as the total number of conductors in the armature and P as number of poles in the DC generator, and also A as number of parallel paths in the DC generator, and N is the speed of armature, speed with which the armature is rotating in RPM, which is nothing but rotations per minute. EG is nothing but the EMF generated in any one of the parallel path. So this is a generated EMF. Let us consider EG as a generated EMF in any one of the parallel paths. So let us consider the flux cut by a conductor. This is the conductor. If the flux cuts the conductor is equals to the flux which is cut by conductor in one complete revolution is equals to the total number of poles multiplied by the flux generated by each pole, which is nothing but P into phi of each pole. If we calculate the flux cut by the conductor in 60 seconds, so we get 1 minute, we get 60 seconds for 60-second time period. If we consider N as the speed of the armature in RPM, the flux cut by the conductor in 60 seconds is nothing but one complete rotation is nothing but we can give it as P into phi into N divided by 60. So the average EMF in one conductor can be taken as P phi N by 60. If we consider the number of conductors in each parallel path, Z by A, the conductors in each parallel path, then your EMF equation turns out to be the number of conductors multiplied by the average EMF generated in a conductor in 60 seconds, which is nothing but P into phi N Z divided by 60A. P is the number of poles in the number of poles in the DC generator. Phi is the flux generated by each pole in the DC generator. N is the speed in RPM. N is the speed of armature, which is given in RPM. And Z will be the number of conductors under each parallel path under the influence of each pole. And A is the number of parallel paths. So your EMF equation will be given as P into phi into N into Z divided by 60 into A. So summary of today's class, we have first discussed about what is the working principle of DC generator, under which we have seen the different cases of Faraday's laws of electromagnetic induction. We have analyzed two cases when the magnet is stationary and the magnet is rotating. And what is the respective EMF equation? Then we have seen the dynamically induced EMF in DC generator. What are the different instances of rotation of the coil and the respective EMF equation? Rotation of conductor or coil under the influence of magnetic field. Then we have seen types of armature windings. Then we have discussed about what is the EMF equation of an DC generator. Today we have discussed about working principle of DC generator. Then we have seen different cases of dynamically induced EMF. And we have analyzed what is the amount of EMF generated for one complete rotation of a conductor. Then we have seen types of armature windings. Then we have also discussed about EMF equation. Of a DC generator. Thank you.